Alright, Chapter 6 Chemical Equilibrium. We've reached the final chapter. And Chapter 6 is not so long compared to other chapters, so we can finish it quickly. So this chapter basically deals with chemical reactions and apply what we have learned so far up to Chapter 5, all the thermodynamic knowledges for chemical reactions. When there is a chemical reaction, after a certain time, chemical equilibrium occurs, right? And at equilibrium, reactants and products would have certain compositions, okay? And we know that from previous chapters that at equilibrium, they exhibit minimum Gibbs energy, right? So from that fact that at equilibrium minimum Gibbs energy occurs, we can determine the equilibrium condition, especially composition of reactants and products. Okay? So for the first several sections, we'll consider those parts, and then we'll apply all these knowledges about chemical equilibrium to real applications, especially in electrochemical cells. Okay? Electrochemical cells is tools to make electrical work based on composition change. Okay? So we'll apply thermodynamic knowledge to electrochemical cells as the final sections of Chapter 6. Okay? So in Chapter 6, we'll consider Gibbs energy minimum at equilibrium, okay? Especially in chemical reaction after it reaches chemical equilibrium, okay? And we'll consider the details about this chemical equilibrium in several specific examples. Also, we'll consider the change of equilibrium under different conditions, such as pressure change, temperature change, etc., and we'll apply that to a specific example. Alright, spontaneous chemical reactions. Okay. So chemical reactions tend to move towards a dynamic equilibrium. We know that, right? So we'll apply those knowledge about equilibrium and we'll determine the equilibrium composition. So to do that, let's consider a very simple chemical reaction. A reactant is A and product is B. Okay? And from previous chapters, we learned that direction of spontaneous change, if there is chemical reaction at constant temperature and pressure, lowers Gibbs energy, right? Then, to determine the equilibrium composition of this reaction mixture, what we need to do is calculate Gibbs energy, okay, of the reaction mixture. And we determine when we get the lowest Gibbs energy and the composition at which the Gibbs energy is lowest is the equilibrium composition. Okay, very simple, right? Alright, so let's consider an equilibrium of A to B. Here's the whiteboard. Okay. Alright. So we'll consider a very simple chemical reaction. A to B. A is the reactant, B is the product. Okay? Alright. Then we assume that the extent of reaction is psi, a constant. Okay? How much reaction occurs. Okay? And let's assume that for an infinitesimal amount of conversion, d psi, okay, which means that the psi of reactant A, the psi of A turns into B, the product. Okay? If you represent this using equations, which means that change of number of moles of reactant A, the Na, should be equal to minus the psi, right? And change of number of moles of product B should be plus the psi, because the psi is the extent of reaction. So this amount of A converted into B, right? So the Na should be equal to minus d psi, and B should be equal to plus d psi. Okay? So for this kind of reaction, this kind of chemical reaction, we define the reaction gives energy, denoted as delta R, reaction energy, G. The reaction gives energy is defined as gives energy change as a function of degree of the extent of reaction at constant pressure and temperature. Okay, this is the definition of reaction gives energy. Okay? Alright? Definition of reaction gives energy. Okay. So if you recall, the change of Gibbs energy as a function of composition should be equal to mu A dNA plus mu B dNB, right? Remember, okay? How Gibbs energy changes as a function of composition, okay? And since dNA is equal to minus d psi and dNB is equal to plus d psi, what you get is mu B minus mu A d psi. Okay? dG is equal to mu B minus mu A d psi. So, basically you get this. How Gibbs energy change as a function of psi, the extent of reaction, which corresponds to reaction Gibbs energy, is mu B minus mu A. Chemical potential change, chemical potential difference between reactants and products. Okay? So basically, reaction Gibbs energy represents the chemical potential difference between reactants and products at the composition of the reaction mixture. Okay, let's move on to the next slide. So, if you look at the next slide, titled exergonic and endogonic reaction. So, reaction Gibbs energy was mu B minus mu A. Okay? So if you plot, so reaction Gibbs energy is defined as round G, round psi at constant pressure and temperature. So if you plot Gibbs energy change as a function of psi, extent of reaction, okay. For example, if Gibbs energy changes something like this, on this region, round G, round psi means the slope of this curve, right? Which is negative. Okay? If this is negative, then mu A is larger than mu B. Okay? Then as you all know, Gibbs energy tends to lower value. So A with higher chemical potential would change to B with lower chemical potential. Okay? Which means that the forward reaction from the original reaction was this, right? The forward reaction would be spontaneous. When reaction Gibbs energy is negative, forward reaction is spontaneous. And this reaction is called exergonic reaction. Exergonic. Okay? So forward reaction. On the other hand, in this region, the slope is positive. Okay? Reaction Gibbs energy is positive, which means that chemical potential of A is smaller than chemical potential of B. So in this case, the reverse reaction is spontaneous, and that reaction is called endogonic reaction. Okay? Endogonic reaction is the reaction at which reverse reaction is spontaneous. And finally, when reaction Gibbs energy is zero, they reach equilibrium. This chemical reaction reaches equilibrium. Okay? So basically it shows how chemical potential changes as a function of composition. Okay. Alright. Description of equilibrium. So from previous chemical reaction, reactant is A and product is B. Let's just assume that A and B are perfect gases. Alright, then reaction Gibbs energy was same as mu B minus mu A, chemical potential difference. And for perfect gas, chemical potential is represented as chemical potential at standard pressure plus RT ln P. Right? So mu B can be represented as this, and mu A can be represented as this. Okay? Which can be rearranged to this. Here, delta Rg naught, same as mu B naught minus mu A naught, right? Reaction Gibbs energy, basically standard reaction Gibbs energy, okay? And RT log PB over PA, basically the ratio between ratio of the partial pressure of product and reactant, which can be denoted as Q here. Q is a kind of reaction quotient, right? The ratio between reactant and product. Okay? So reaction Gibbs energy, delta Rg is equal to standard reaction Gibbs energy, delta Rg naught plus RT ln Q. Okay? Then at equilibrium, now is an important point. At equilibrium, we learned that reaction Gibbs energy is zero, right? So 0 is equal to delta Rg naught plus RT ln K. Here, the reaction quotient Q is replaced by K because we use K, which is equilibrium constant, right? Which is basically the reaction quotient at equilibrium, right? Same meaning, but K represents the reaction quotient at equilibrium, right? So delta Rg plus RT ln K is equal to 0, right? So if you rearrange this, we got this expression. RT ln K is minus delta Rg naught. This is a very important equation because standard reaction Gibbs energy can be determined based on thermodynamic knowledge that we have learned so far. Basically, this is thermodynamic data. And on the left side, L and K, equilibrium constant. Equilibrium constant is about compositions of reactants and products. It's about chemical reaction. So this simple equation basically shows the link between thermodynamics and equilibrium constant. Right? Okay? It's a very important equation. Okay? If you want to interpret this in molecular level, okay, why Gibbs energy shows a minimum as the reaction goes. Right? Okay. Basically, reaction Gibbs energy actually is sum of entropy and enthalpy terms, right? Okay? If there is no entropy term, basically if there is no mixing effect of reactants and products, then Gibbs energy would change like this or like this, depending on the reaction, if it is exothermic or endothermic, right? And we have learned that Gibbs energy of mixing has this form, okay? So if you plot Gibbs energy of mixing as a function of extent of reaction, it looks like this, right? And mixing is basically based on entropy effect, right? So if you combine entropy term and enthalpy term, we finally get this Gibbs energy change as a function of extent of reaction. Okay, so basically this Gibbs energy change as a function of extent of reaction is a result of both enthalpy and entropy. Okay. Okay, so minimum in Gibbs energy is both reaction and mixing effect. Okay. General case of a reaction. We only consider very simple reaction, right? From A to B, A was a reactant and B was a product. Okay? How about if you consider much more complicated or general chemical reaction, such as 2A plus B changes to 3C plus D? Okay. We can use the same expression, right? Basically same equation as shown here. Reaction Gibbs energy delta RG is equal to delta RG naught plus RT and Q, right? And here standard reaction Gibbs energy can be determined if you have an information about molar Gibbs energy of each of reactant and product, right? And molar Gibbs energy basically represents the formation Gibbs energy, right? So if you have an information about formation Gibbs energy of reactants and product, then by simply multiplying by reaction quotient, like 2, 1, 3, 3, 1, something like that, you can determine this reaction, a standard reaction Gibbs energy, right? Okay, and Q is, as you have saw, is reaction quotient, okay, which has a form of multiplication of activities of product and divided by activities of reactants, something like this. So, for example, for gas, the activity can be represented as partial pressure, right? So, to calculate Q, for gas, you can use partial pressure. For liquid, you can either use mole fraction or concentration, something like that, right? Okay. And especially for pure solid and liquid, activity is considered 1. So we don't really need to worry about calculation of Q, especially for pure solid and liquid. Okay, so let's derive this, if this is really true for general chemical reaction. Alright. Let's derive that. Okay. So for general chemical reaction, with extent of reaction is the psi, and for each species, reactant and product, stoichiometric numbers are mu j. Okay. Then the amount of reactant and product change by this chemical reaction, by this extent of reaction, the Nj can be written as mu j d psi, right? If you recall, for this simple reaction, the Na was minus d psi, the Nb was plus d psi, right? Because A is reactant and B is product. Okay. Similarly, if there is a general chemical reaction, then for reactants, the Nj will be minus, right? Because this coefficient is minus. For product, the Nj will be positive, right? Okay. So then, chemical Gibbs energy change, by definition, is sum of mu j d and j, right? And the nj is same as this, so we can sigma mu j d psi. Okay, since d psi is not relevant to this sigma, you can put parenthesis here. Okay, which correspond to reaction Gibbs energy. No, sorry. Okay, keep it here. Okay, and total Gibbs energy change is defined as reaction Gibbs energy times d psi, right? Okay, total Gibbs energy is reaction Gibbs energy times d psi, because reaction Gibbs energy was defined as g round psi. Okay. Okay. So, which means that this part and this part are same. Okay. So reaction Gibbs energy delta G is equal to sigma mu j, and by definition, chemical potential can be represented as chemical potential as standard pressure plus RT natural law AJ for general expression. Okay, activity. Okay. If you rearrange this, sigma mu j not plus RT sigma mu j log AJ. Okay, and this part corresponds to reaction Gibbs energy as standard state, basically standard reaction Gibbs energy, plus, since we have log here, log, this constant can be moved to here, right? Okay, so RT sigma log AJ mu j. Okay, then since there is a sigma for log, if you sum up many different kinds of log, you basically multiply by this, right? Which is pi aj nu j. Okay, and this part is basically same as q, right? Okay. Okay, you derive the relation between chemical equilibria and reaction gives energy. Okay? Alright. So basically, if you want to calculate reaction quotient Q, what you need to do is you basically do this. Okay? 4 reactants, 4 products. Okay? And especially if the reactant or product are pure solid or liquid, then activity is 1, so you don't really need to worry about. And as I mentioned, activities can be, this activity AJ can be represented as partial pressure if it is gas, such as Pj over P naught, right? Or concentration, right? Molar concentration, for example. Then concentration over standard concentration, okay? Or molar concentration. Then Bj over B naught, right? Okay. Here, standard pressure P naught is something like 1 bar, and C naught is something like 1 mole per liter. B naught is something like 1 mole per kilogram. Okay, standard pressure, standard concentration, something like that. So if reactant or products are gas, then activity can be represented as partial pressure. If they are solution, then they can either be expressed as molar or molar concentration. Okay. All right. Okay, let's move on. The relation between equilibrium constant, I just skip this part, it's not that important. So let's move on to the response of equilibria to pressure. Okay. Response of equilibria to chemical at the pressure. So for chemical reaction, they tend to move toward dynamic equilibrium, right? And let's say that a certain reaction is at equilibrium. Okay? Then, what if there is a change of condition outside, such as pressure, temperature, or concentrations of reactants or products? Okay? I believe that you guys all have learned this from general chemistry class. So let's review it. Okay? What would happen if there is a change of pressure or temperature or concentration of reactants and products? Okay? One important thing is that equilibrium changes basically. The response of equilibrium. Equilibrium changes if something happens to the chemical reaction at equilibrium, right? Pressure, temperature, or concentrations. But one important fact is that equilibrium constant K, only depends on temperature. Okay? The reason why is that, let's review. Let's go back to the previous slide. Okay. Equilibrium constant. Here, K, RT ln K is equal to minus delta R G naught. Okay. This is standard reaction Gibbs energy, right? So the reaction Gibbs energy as standard state. Okay. So it's basically a certain number for a specific chemical composition, right? R is constant. T, K only depends on T. Okay, there is no pressure term, there's no concentration term whatsoever. Okay, so only temperature change can change the equilibrium constant. Okay, that's very important fact. Okay, you have to remember, only temperature can change the equilibrium constant. So, if pressure changes, equilibrium constant does not change. That's the constant, K. It does not change. Okay? Then let's consider what happens if pressure changes. Let's say that we increase pressure for a specific chemical reaction. Okay? We can increase the pressure either by injecting inert gas or by decreasing the volume by compression. Either way, we can increase the pressure and see what happens. Okay? So, for example, let's consider this equation, this chemical reaction. Reactant is A, product is B, 2B, and both of them are gases. Okay? Okay? And let's express chemical equilibrium constant K for this chemical reaction. Okay? Let's do it. For this reaction, K can be expressed as activity of A and activity of B square, right? Because there is a number 2 here, right? At equilibrium. Okay? And since both of them are gases, activity basically can be represented as partial pressure, right? So A is PA over P naught, and AB is PB over P naught square, okay, which corresponds to PB square over PA P naught. Okay. And as I mentioned, let's say that we increased pressure. What would happen? How would the equilibrium change? One very important thing is K does not change even though we change the pressure. So K should be constant, which means that this should be constant. Okay? But we increase the pressure either by injecting inert gas or by compression. Then both PA, PB would increase, right? Because total pressure increases. Okay? But this should remain constant. Okay? Even though PA and PB, both of them increases. Okay? Then what should happen? What should happen? Both PA and PB increases, but this term should remain constant. Then PA should increase much more than PB, right? Because PA is in the denominator of this equation, right? And PB has this square, right? So PA should increase much more. Okay? To do that, to make this happen, reverse reaction should occur. The equilibrium should change in the reverse direction, right? Okay? To make this happen, to make this value constant, reverse reaction should occur. Okay? This is the example of Le Chatelier principle. You know, all of you remember from general chemistry class, right? Le Chatelier principle, okay, which say that a system at equilibrium, when subjected to a disturbance, responds in a way that tends to minimize the effect of this disturbance. Okay? So, for this reaction, we increase the pressure. And to maintain the equilibrium, it responds in a way that tends to minimize the effect, minimize the pressure increase. To do that, we have to decrease the number of molecules. One molecule, two molecules. Right? So we have to, this chemical reaction, this equilibrium, should move in reverse direction. Okay? Alright. Actually, you can do it more quantitatively for the same reaction, how much reactant A and how much product B changes as a function of extent of reaction. Okay. So I'll just skip this part. So please do this derivation by yourself. Okay. Next response of equilibria is to temperature. Okay. Same principle applies. Same Le Chatelier principle applies. But the important thing is, when temperature changes, equilibrium constant also changes, right? Before do that, according to Le Chatelier principle, okay, let's see what happens. If the reaction is exothermic, so basically by reaction, heat is generated, right? So, for exothermic reaction, if we increase temperature, what would happen? The equilibrium would move toward to minimize this effect, to decrease the temperature, right? To do that, reverse reaction should occur, right? So increased T would favor the reactants, okay? On the other hand, if the reaction is endothermic, okay, by chemical reaction, it absorbs heat from surroundings, okay? Then if you increase the temperature, okay, that should try to minimize the effect of this increased temperature. That's fold reaction. So it should favor the products. Okay? To describe the Le Chatelier's principle for the temperature change, especially quantitatively, we can simply derive an equation called Van Hoff equation. Okay, how equilibrium constant changes as a function of temperature, right? Okay. All right. Let's start from here. From previous equation, that right? Reaction gives energy. Standard reaction gives energy is minus RT ln K. You start from here. Okay. And if you take the derivative on both sides as a function of temperature, okay, what you get is on the left side you get d ln K over dt, and on the right side you have an expression for standard reaction gives energy over T. if you take the derivative of Gibbs energy over T as a function of temperature, what you get is minus enthalpy over T squared, according to Gibbs-Helmholtz equation, right? Remember Gibbs-Helmholtz equation? Okay? So you can simply have this expression. Very easy, right? So if you integrate both sides by moving dt over this side, you can simply get this expression. At two different temperatures, if equilibrium constant is K1 at T1, K2 at T2, then ln K minus ln K1 is equal to minus standard reaction enthalpy over all T2, 1 over T2 minus 1 over T1. Which means that from this reaction, from this equation, if you have an information about temperature and equilibrium constant at one temperature, then you can determine the equilibrium constant at another temperature. Okay? Right? If temperature changes, equilibrium constant changes, and we can determine how much it changes using this equation. Okay? It's also a very important equation. Okay? Alright, so this is the end of section 6.4. Okay, now move on to final sections. Section 6.5 to 6.9. So, from section 6.1 to 4, we discussed the general knowledge about chemical equilibrium. And we'll apply those knowledge to an important specific example, which is electrochemical cell. Okay? Alright. So simply let's introduce what electrochemical cells are, their principle, how they look, and how we can apply thermodynamic knowledge to the working principle of electrochemical cells. Okay, so electrochemical cell consists of basically two electrodes and electrolyte. Very simple. So basically it looks like this. Two electrode, anode and cathode, and electrolyte. Electrolyte can be shared by these two electrodes, or it can be separately used. Okay, so you might be familiar with this kind of diagram, right? Very simple, right? Electrochemical cells consist of two electrodes, usually metallic conductors, and electrolyte. Electrolyte is ionic conductors, right? Okay. So depending on the type of electrode, it could either be metals, or it could be gas, or metal insoluble salt, etc. There are many different kinds of electrode. Okay. And overall, electrochemical cell can be divided into two different kinds: galvanic cell and electrolytic cell. Galvanic cell is an electrochemical cell which basically generates electrical energy by spontaneous reaction. And on the other hand, electrolytic cell is a cell which makes electricity basically based on non-spontaneous reaction. So to make electrolytic cell working, we need some energy input. Okay, so there's two main kinds of electrochemical cell. And electrochemical cell, basically there are two different kinds of reactions occur, right? Oxidation and reduction. Everybody knows what those are, right? Oxidation is a reaction in which electrons are removed. Well, right? On the other hand, reduction is based on addition of electrons, right? And we call redox reaction, right? A reaction in which there is a transfer of electrons. Okay. All right. And usually, for electrochemical cell, we express all the redox reaction as reduction reaction, right? That reduction reaction is called half reaction. Okay? So for example, half reaction for the reduction of Cu2 plus can be represented as this, right? Cu2 plus 2E minus electron goes to solid state Cu, copper, right? Similarly, for zinc 2 plus ion plus 2E minus electron goes to solid state zinc. Okay? So we basically express all the redox reaction as half reaction, as reduction reaction. Then you combine it by subtracting one reaction by another. For example, if you subtract this reaction from this reaction, then you can get this redox reaction, right? Here, zinc metal oxidized to zinc 2 plus. On the other hand, Cu2 plus ion reduces to solid Cu, something like that. So basically, we express all the reaction as conceptual half reaction, and we express basically all the redox reaction as the difference between these two different kinds of half reaction. Okay? Alright. And for half reaction, the reaction quotient Q can be expressed as this, right? Because this ion has activity, electron does not have activity, so we don't really need to worry about electrons, and pure solid has activity of 1. So simply we can express reaction quotient for half reaction as this. Okay? This is the simple case. If it is a little more complicated, if it is a little more complicated, we can express it something like this. Okay. For example, if the redox reaction is something like this, or 2 gas plus 4H plus AQ plus 4E minus goes to water. Okay. Sorry. For this reaction, gas, ion, electron, and liquid, reaction quotient Q can be expressed as AO2, right, times AH4, right, 4H4 plus. And for electrons, we don't really need to worry about. And for pure liquid, activity is 1, right? Okay. And activity of gas, oxygen, can be expressed as P oxygen over standard pressure, right? And activity of hydrogen ion can either be expressed in molar concentration or molar concentration. So for example, like H plus molar concentration for something like that. Okay, so you can easily express reaction quotient even for redox reaction. Okay. All right. Let's move on. Reactions at electrodes. So what kind of reactions occur in electrochemical cell? Oxidation and reduction, right? And it's very simple. There are 2 electrodes, right? Anode is the electrode at which oxidation occurs. Okay? Cathode is the reaction electrode at which reduction occurs. Oxidation anode, reduction cathode. That's all. Okay? So if oxidation occurs on this electrode, which means that, for example, if this electrode is a solid metal dissolves into some solution, some electrolyte solution as ions, right? And it generates electrons, right? Okay? And that electron moves through this circuit and goes to cathode. And at cathode, at which reduction occurs, some ions in the electrolyte solution gains these electrons and reduces, right? Okay? Okay, so anode is oxidation electrode, cathode is reduction electrode. Okay. So there is a sign here, minus sign and plus sign here, right? So minus sign represents the electrode at which electrons leave the cell. Electrons leave the cell through this circuit, right? So this side is minus, and this side, when at which electrons enters the cell, is positive. Okay. So if this is a galvanic cell, which is an electrochemical cell which generates electricity based on spontaneous reaction, right? Since cathode is positive, okay, which means that cathode has higher potential, higher electric potential compared to anode, right? We'll get back to that point again. Varieties of cells. There are many different kinds of electrochemical cells. Daniel cell, electrolyte concentration cell, electrode concentration cell, etc. Depending on the type of electrolyte and depending on how electrolyte is formed with electrode. So you can just read the textbook, okay, about this. Liquid junction potential. Okay. So we commonly encounter this kind of electrochemical cell. Two electrolyte and two electrode and common electrolyte solution. Okay? But in some cases, such as like this electrode has this electrolyte solution and this electrode has this electrolyte solution. Okay? Some cells have different electrolyte for different electrode. Okay? In that case, between these two different electrolyte solutions, there is also electrical potential difference. Okay? Not only between these two different electrodes, but also between these two different electrolyte solutions, there is electrical potential difference. Okay? That potential difference is called liquid junction potential. Okay? So, sometimes we really care about this liquid junction potential because we only need to worry about potential difference between these two electrodes, basically two different redox reactions. Okay, so to remove this liquid junction potential, we usually use salt bridge. I believe that you guys have learned this from middle school or high school, right? Salt bridge. Okay. Salt bridge is basically a tube containing a concentrated electrolyte solution. So basically it completes the electrical circuit between these two different liquids. So by using these concentrated electrolyte solutions, we can not totally, but sometimes highly reduce the liquid junction potential between these two different electrolyte solutions. Okay, notation for electrochemical cell. It's very simple actually. For phase boundary, we use vertical bar, one bar, just one single bar. So for electrode, solid, gas, liquid, solid, right? All has different phases, right? So we put just one single vertical bar. If there is liquid junction, we put 3 dots between them. If we use salt bridge between these two liquid junction, we use double vertical lines. Here, this is wrong. We have to put just one line here, right? So this is all, right? Single bar for phase boundaries, 3 dots for liquid junction, and 2 vertical bars for salt bridge. Now let's move on to the important parts, the cell reaction and cell potential. Okay. We'll primarily consider only galvanic cell, okay? Basically generating electricity based on spontaneous reaction. It's simple because there is a rule to express galvanic cell. There is a rule. The rule is we put cathode at which reduction occurs, cathode on the right side. So this is cathode. And this is anode. That's the rule. When you express galvanic cell using the notation of electrochemical cell, we put cathode on the right side and anode on the left side. Okay? And cathode is reduction electrode. Anode is oxidation electrode, right? Okay. So on each electrode, cathode and anode, we write half reaction cell. Half reaction, not cell, half reaction. So on the cathode, half reaction is this, right? Reduction of Cu2 plus to solid Cu, right? On the left side, on the anode, half reaction is this, right? Okay? And since on the cathode reduction occurs and on the anode oxidation should occur, right? So simply what you do is you subtract these two. You subtract this half reaction from the first reaction. Then you get this. This is the redox reaction which occurs at this electrochemical cell. That's all. Very simple, right? It's just a rule. On the right side, you put cathode. On the left side, you put anode. You write down half reaction on both electrode, and you subtract it. That's all. Okay? Alright. That's pretty much all for cell reaction. And for any galvanic cell, there will be a cell potential, okay, which measured in volt, right, as in battery, right, okay, and that cell potential, okay, basically represent the Gibbs energy of that chemical reaction occurring in the electrochemical cell. Okay? Then we'll derive this, why this is true. Okay? From chapter 6.1 to 4, we learned about reaction Gibbs energy. Okay? Gibbs energy change as a function of extent of reaction. Okay? And especially for electrochemical cell, that corresponds to cell potential, electrical energy, electrical work, basically. Okay? And let's derive it. Why it is true. And how electrical potential of electrochemical cell is related to reaction Gibbs energy. Okay? Actually, just let's first look at the result. This is the result. Okay, reaction Gibbs energy corresponds to minus nu Fe. Here, E is electrical potential of electrochemical cell. Okay, so they are related by this simple equation. Okay, here nu is the number of electrons of the specific chemical reaction, especially for electrochemical cell, and F is Faraday constant. Okay, and let's show why this is true. Okay, let's show that why this relation is true. Alright. Okay, it's actually very, very simple. by definition, dg is equal to reaction Gibbs energy times the psi, okay, or the psi of the extent of reaction, okay, and dg is equal to the WE from chapter 3. Gibbs energy has a meaning of maximum non-expansion work. Okay, remember? Maximum non-expansion work. Okay? And the electrical work generated by this electrochemical cell is non-expansion work. Right? Basically, a work generated by change of chemical composition. Right? Okay? And we'll have this. Okay? Right. So, here, the psi is the extent of reaction, right? Then, nu d psi is the amount of electrons which have been moved from anode to cathode. So here, nu is the number of electrons from redox reaction. For example, for this half reaction, nu is 2 here, right? That's nu, right? So, if the extent of reaction is d psi, total amount of electrons which have been moved from anode to cathode corresponds to nu d psi, right? Okay, this is the amount of electrons. Okay. Then, how about total charges which have been transported by these moving electrons? Okay. So the amount of electron is mu d psi. Okay. Okay. And one electron has charge of 1e, right? E, which corresponds to 1.6 times 10 to minus 19 coulomb, right? So since electron has negative sign, we put minus e, okay? This is for one electron. Then how about per mole? Per mole. To calculate something per mole, you can simply multiply by Avogadro's number. Avogadro's number. Right? Avogadro's number. So by simply multiplying the amount of electrons, electrical charge of one electron, Avogadro's number, right? 6 times 10 to 23rd per mole. Okay? So this corresponds to total amount of charge. Okay? And interested is E, single electron charge, times Avogadro's number corresponds to, not definition, corresponds to Faraday constant. You might remember this, like 96,500 coulomb per mole, something like that, right? Okay, that's Faraday constant. So total charge is actually minus nu f d psi. Okay. Now, what we want to calculate is the amount of electrical work. Electrical work is basically charge, total charges, times voltage or electrical potential difference. And total charge is minus nu f d psi. And voltage is electrical potential, E, okay? That should be same as this, delta RG dxi, okay? dxi, dxi. So now we get reaction Gibbs energy corresponds to minus nu F electrical potential, okay? Alright. So please do derivation by yourself. Okay? Alright, let's go back. Let's go back to the next slide. There's the equation. Actually, let's just use the whiteboard again. Sorry. So we got, what you got is reaction Gibbs energy is minus nu F E electric potential. Okay. And from previous sections, we got reaction Gibbs energy is equal to standard reaction Gibbs energy plus RT ln Q. Okay? Then we can put this here. So minus nu Fe is equal to minus nu Fe naught. Let's denote it as standard electrical potential plus RT ln Q. Okay? So here E naught is equal to minus nu F G naught, okay? So if you rearrange it as a function of electric potential, E is equal to E naught minus RT over mu F ln Q, which is called Nernst equation, okay? Basically relates reaction quotient and electrical potential generated in electrochemical cell. Okay? Especially at equilibrium. At equilibrium. Since E is 0, okay? Because at equilibrium this is 0, right? So what you get is E naught is equal to RT over mu F ln K. Okay? Which is very important. So this is very important. Basically relates standard electrode potential and equilibrium constant. Okay? Equilibrium constant is determined based on chemical reaction at equilibrium, compositions, right? Electric potential can be measured by using voltmeter for electrochemical cell. That this equation basically relates these two variables. Okay? So which is very important. All right. So this electrode potential can easily be measured by using a certain reference. Basically, we are measuring the voltage, right? To measure voltage, there should be voltage difference. Okay? And if you have a certain reference as voltage of 0, then you can easily determine the difference between the reference and a certain electrode, right? So there are many different kinds of references, and usually we use standard hydrogen electrode, which is like this. The details are not important. We just use standard hydrogen electrode as 0 volt. Okay? And for other types of electrode, like this one, or any other types, we simply connect this electrode and another electrode, and you measure voltage, and you can determine easily the voltage difference or the standard electrode potential of a certain electrode. Okay? Alright. I'm going to skip this part, it's not that important. So by basically measuring that electrical potential, we can determine standard potential of a certain half reaction, right? This electrode is the reference point, which has a 0 volt, and by simply connecting this and this, or this and this, something like that, we can determine the standard electrode potential. Okay? And one thing very important to determine standard electrode potential of an electrochemical cell is that standard potentials are not changed even if the chemical equation is multiplied by a numerical factor. Okay? Let's see an example. An example. Okay. Common example for this cell. Common redox couples, right? Okay. If you recall, you put cathode on the right side, anode on the left side. Okay? Something like that. Okay? And you write down two half reaction. First at the cathode, Cu2 plus on the anode, sorry. And you subtract it. Okay? Then you get this reaction, right? Okay. And to determine the electrode potential of this electrochemical cell, okay, how can you do it? The electrochemical potential of this half reaction is given in the table, right? Which is plus 0.34 volt. For this half reaction, electrode potential is minus 0.76 volt. And total for the resulting electrochemical reaction, the resulting standard electrode potential for this reaction will be this minus this. Plus 0.34 minus 0.6, which corresponds to plus 1.1 volt. That's the standard electrode potential for this reaction. Very simple, right? Okay. In this example, we didn't really need to worry about number of electrons, right? Because there was only, there were two electrons on both equation, right? But for example, let's say that we are using sodium instead of zinc. Okay. Here in the table, electrode potential for reduction of sodium ion is minus 2.71 volt. Then to subtract these two reactions, what you need to do is you need to multiply by 2 both sides and subtract it, right? Then you get what you get is 2NaS plus Cu2 plus goes to 2Na plus CuS. Okay, you multiplied by 2 on both sides, but you should not multiply by 2. Okay, what you need to do is simply subtract it. Then you get plus 3.05 volt. Because standard electrode potential is an intensive property. Okay? Because standard electrode potential was related to what? Equilibrium constant, right? There is also intensive property. Energy. Okay. So, since standard electrode potential is intensive property, you should not multiply by 2. Okay? Intensive properties properties at which it does not depend on the size of the system, right? Okay. The reason why is that if you multiply by some numerical factor, it also increases reaction Gibbs energy. Okay? And reaction Gibbs energy is related to electrode potential. But since you multiply by some number and that increased the reaction Gibbs energy, so it cancels out. So it does not change. Okay? So that's one important thing that you should remember to calculate the standard electrode potential of a certain electrochemical cell. Okay, finally, how or where can we apply this standard electrode potential? Where can you use this information? There are several applications. Okay, the first one is electrochemical series. By simply looking at this number, this volt, right? What kind of information can you get? That's actually been determined from this relation here. If standard electrode potential is positive, this is positive for a certain electrochemical cell, then K is positive. K is large and positive, which means that a certain chemical reaction moves toward forward reaction, right? Okay, forward reaction is spontaneous reaction if E standard electrode potential is positive. Okay? Okay? If this is negative, this is smaller than 1. Okay? If this is negative, this is smaller than 1. Which means that K, since K is smaller than 1, the reverse reaction is spontaneous. Okay? Forward reaction cannot occur spontaneously. Okay? So depending on the sign of electrode potential and also how large the number is, we can determine the direction of chemical reaction. Okay? And also spontaneity. Okay? So that basically determines the electrochemical series. Okay? So if you have this kind of numbers for different metals, cesium, copper, silver chloride, zinc, sodium, something like that, the reaction, the half reaction with the minus side, like this basically at the bottom, is much more reducing, which means that this metal can much more easily oxidized compared to other metals, right? So from this table, from this series, the one at the bottom is much more reducing one. On the other hand, on the top, much less reducing. So I believe that you guys have learned this from middle school or high school, right? Which is called trend in ionization, right? Potassium, calcium, sodium, magnesium, aluminum, chromium, zinc, something like that. You remember, right? Kalium, actually. You call it kalium, right? Kalium, calcium, natrium, magnesium, something like that, right? Okay. That is based on this electrochemical, the standard electrode potential, right? That's the first example, first application of standard potential. Okay. Next application is you can determine activity coefficient based on electrode potential, based on actually this equation, but that's not important because because this electrochemical cell has certain redox reaction that should involve activity, right? And activity has activity coefficient. So basically, using electrode potential, you can determine activity coefficient, but it's not important. Third application is based on this equation. If you have information about standard electrode potential, you can determine the equilibrium constant. Right? That's obvious, right? And finally, if you have information about standard electrode potential, which means that you have information about standard reaction Gibbs energy, right? If you have information about Gibbs energy, you can determine entropy and enthalpy, right? Simply, right? Because entropy is how Gibbs energy changes as a function of temperature, right? You can simply determine it. And if you have information about Gibbs energy and entropy, then you can determine enthalpy. That's pretty much all. Okay? So based on knowledge about standard electrode potential, you can have several applications you can use. Okay? So this is the end of chapter 6 and all of this class. So you guys have done well, and let's meet at the class.